Mathematics at Western Ontario University. He was formerly head of their theoretical physics project as well. Chris has been convening meetings annually in Iccc, Italy, on the limits of climate forecasting. He's thrown his mathematical knowledge into the climate arena, and he has two phenomenal things going for him. He has been criticized in the Parliament of the Canadian government as being a climate denier. That's certainly a feather in his cap. And secondly, he studied scientific heresy under the famous Freeman Dyson at Princeton University. So he comes very well qualified for this talk. Chris?
Okay, so I'm going to need some technical assistance here. Yeah.
Is our computer person here? Whoops.
I need to find the USB hole.
Okay,
where is it?
Probably on this side. There we go.
Left-hand side, sir.
There.
For USB stick, I'll take it.
For some reason they screwed it up. Didn't go.
It'll take a second while I pull it right to the desktop.
Just so you know, I did submit this.
That's what they always say.
Under Freeman Dyson, I merely got advice from him on how to be a climate heretic. My thanks to the organizers for asking me to speak today. I'll begin with the second part of my title. It comes from a remark by Albert Einstein. In the realm of seekers after truth, there's no human authority. Whoever attempts to play the magistrate there founders on the laughter of the gods. The magistrate for the truth of climate is the UN, of course. Who else could it be? And consistent with Einstein's remark, the gods started laughing the instant the UN took the job. They've hardly stopped since. In this talk, I cannot hope to describe the full scope of the climate madness that we have endured these past 20 years. It will take decades for historians to sort it all out, and there's still plenty of insanity in the pipeline. For example, it was recently a fad to call for the trial of we climate criminals. This cartoon from the Toronto Sun responds to a well-known environmentalist who called for prison sentences. Of course, there are a number of prominent names here in the US and in the UK who have been behaving as foolishly. And I won't even bring up the actual trial of Bjorn Lomborg. I'd like to take just a moment to convey my respect to all those who, over the last 20 years, stood their ground against the madness, often completely alone, and with all the cards stacked against them. There are many lonely tales of civil courage and personal suffering that I believe one day will get a fair hearing. If this was just about a scientific consensus, there would be no consequences for its critics. Scientists are supposed to question things. It's their job. However, if you are a scientist thinking about coming out to do your job, I advise you to first consider these words of George Orwell. Anyone who challenges the prevailing orthodoxy finds himself silenced with surprising effectiveness. A genuinely unfashionable opinion is almost never given a fair hearing, either in the popular press or in the highbrow periodicals. Instead of a scientific consensus, there's an Orwellian orthodoxy maintaining that there is a scientific consensus. True believers usually have no clue who is part of or what was agreed to in the scientific consensus that they believe in. Although for the most part, this has been a David versus Goliath situation, we climate criminals have actually had the upper hand. We know, unlike the others, that no one really understands climate. Power, money, and fame can't change that. Consider this quotation. In climate research and modeling, we should recognize that we're dealing with a coupled, nonlinear, chaotic system, and therefore that long-term prediction of future climate states is not possible. This remark seems like something from the Radical Climate Denier's Handbook. It's so radical that even I see it as a bit extreme. But we climate criminals did not write it. Ladies and gentlemen, I give you the scientific consensus of the UN. Can you hear the laughter of the gods yet? I've been hearing it for a long time. I was invited not long ago to give a talk at another conference on climate. Afterwards, a participant approached me with a complaint. He thought my rather technical talk was not useful to his work. He seemed to be on a higher mission from policymakers. I skipped a retort and simply asked him what his work was. His job was to create closure schemes for ocean turbulence. While I knew what that was about, there's something surreal about such a field. In case you don't know, the closure problem of turbulence is among the great unsolved problems in science. Some of the greatest minds in history have been trying unsuccessfully to crack it for over 100 years. But here's this guy who doesn't just solve it once, but routinely. Such claims would seem preposterous. However, suppose I tell you he did this impossible thing for big general circulation computer climate models. I'll bet that some will shrug and say something like, well, seeing as it's for climate models, it's okay. Now, personally, I'm with Alice when she tells the Queen in Wonderland that one can't believe in impossible things. But if you're in the climate modeling business, you have to believe, like the Queen, in 6 impossible things before breakfast. Climate modeling is a unique and extreme case on many levels, not only because of the enormity and complexity of the problem itself, but also, and just as significantly, because of the staggering naivete about computing among educated people. Many of them believe that what comes out of such models is not simply data, but future observations. I call this the Clockwork Fallacy, because they see computers as moving us forward to the 17th century. That was when people saw the universe as a giant, predictable clockwork. Add Hollywood computerized special effects to the mix, and the clockwork believers imagined that shovels full of equations from classical physics get dumped into a hopper at the top of a climate model Cuisinart, which produces tasty and accurate solutions at the press of a button. The reality, however, is much different. Instead of a sleek kitchen appliance, think of a huge, roaring, smelly 18th century steam engine, shaking and sputtering with enormous flywheels turning as an army of terrified tenders dart for their lives between huge flailing iron lever arms and monstrous gears while choking on smoke and struggling desperately to keep the engine running without its boiler exploding. The mayhem of the thing makes it impossible to even contemplate whether the engine can accomplish anything useful. Now that's a climate model. Climate ties the deepest questions of mathematics and science to the most mundane applications. We get daily weather reports based on differential equations that we actually don't know how to solve. I'm not joking. Even just determining the existence of solutions for these equations, Navier-Stokes, is considered one of the deepest problems in mathematics. And this is in addition to the closure problem already mentioned. In fact, the Clay Mathematics Institute will give you $1 million if you could manage to furnish them with the solutions. You should think maybe of lottery tickets instead. So we don't have the formal solutions, but can we get them from a computer? No. We don't actually use equations on a computer. Think of a differential equation as an egg. Putting it onto a computer is like making an omelet. What actually goes onto a computer is something known as a discrete map, which isn't the original continuous differential equations at all. These maps have solutions in their own right, differing from their original equations. Of course, they're selected to be as close as possible without taking too long to compute. But their errors can be significant and hard to identify. particularly over long times. The maps can have instabilities where there are none, false chaos, and they can also falsely stabilize chaos that's actually there, false stability. Colleagues and I published one of the first examples of the latter in Physics Letters in the 90s. But climate models do not even constitute proper computation in the classical sense. Maps, unlike the equations they approximate, have a grid size associated with them. Pixels on a video screen are an example of such a grid. Anything smaller than the distance between the pixels is lost. The first rule of classical computing, as taught to students, is that the distance between grid points, pixels, if you wish, denoted by the black two-headed arrows, must be smaller than the wiggles in the solution. This is the case in the upper figure, but in the lower one, the grid is much larger than the wiggles. That is what happens in climate models. The wiggles are much, much smaller than the grid. Thus, models violate the first rule of classical computing, making the other problems discussed minor by comparison. But the modelers must do this. If you were to do the computation properly, the grid distance would have to be smaller than the smallest turbulent eddies. That's known as the Kolmogorov microscale. That's about a millimeter. Using that for a grid scale, we can estimate with simple assumptions how long a 10-year forecast would take to compute on a modern computer. How long would you guess such a calculation would take? Some offer 10 years as a joke, but the number comes out to be 10 to the 20 years. That's 10 billion times the current estimate of the age of the universe. While numbers like this are not uncommon in the field of computational complexity, the lesson is clear. There can be no big-time climate models without violating the first rule of classical computing. So what is the grid spacing in the big models? It's not millimeters, meters, or even kilometers. It's hundreds of kilometers. That stunning fact makes all of the weather that we experience too small to show up in climate models. All of it. And that includes the heat transport from ground to space. Leaving these things out would be a disaster for the physics. The fix is to introduce fake physics, like mortar between the bricks to keep the structure standing. The aim of the fake physics is to mimic what Mother Nature does between the pixels, but only faster. I would mention parenthetically that instead of fake physics, the official term is parameterization. I would use that term too if I did not have to endure so many who are sucked in by the clockwork fallacy. You can lose your way in the fake physics because parameterizations can be coded straight into computers without any ideal equations to approximate at all. Some are even driven by random numbers. Climate models are a long way from anything like a controlled computational approximation of established equations. There is one and only one thing that anchors the fake physics, that's observation. Thus, climate models are empirical constructions and not direct implementations of known physics at all. They may at times be inspired by the physics, but that's like saying hamburger chains use 100% pure beef while making the burgers. The consequences of this insight are enormous. For example, if you say, I don't like climate models because their tropospheric temperatures don't agree with observations, then that can be fixed. If you say that there's a problem with cloud amounts, well, that can be fixed too. If you say that climate models rain strangely or they don't agree with each other, well, then you get the idea. It's the nature of empirical models. John von Neumann, one of the fathers of modern computers, among other things, famously said, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. What my ocean turbulence closure friend was doing was working on model parameterization. Should I say that his work was not useful? No. Climate models have a place. There are good and talented people working on them. They make a contribution as long as we don't get overwrought by the mystique of computers. If I were making such models, I would be forced to do exactly the same difficult choices, and then I too would have to believe in 6 impossible things before breakfast. But as I said, I'm with Alice. Unfortunately, despite their enormous limitations, climate models do not play a mere supporting role in climate change research. They are virtually the only game in town. I believe that this would not be the case if the Clockwork Fallacy and policymakers were not setting the research agenda. As things stand, climate models don't just compute climate change, they define it. I have said how empirical climate models with empirical problems can be fixed empirically. In forecasting climate change, climate models part company with legitimate empirically based engineering models. The latter are based on controlled experiments under all conditions envisaged. However, in climate dynamics, we cannot do controlled experiments, and we have little or no precise observational knowledge of what conditions will be encountered in the future. That's because even in the absence of external influences, we cannot presume that the next 100 years will be like the last. We're dealing with a complex nonlinear, chaotic dynamical system. It's one of the most extreme examples we know. Such systems can take any amount of time to explore all possible dynamics. Here's a very simple example of a chaotic dynamical system exhibiting intermittent bursts. After settling down, the first burst occurs at about 500. There are two cases plotted that start out at very close to each other, dots and dashes, but instead of growing apart, the two cases grow tightly together. At each step after 500, or before 500, they stubbornly return the same value over and over. After reading the same value 100 or 200 times, you might be excused if on empirical grounds you expect that you will only ever get one value for both dots and dashes. If empirical boredom captures you, you will be surprised at 500. After the burst, the dashes return to the original values, and the dots, which I've highlighted in red, jump to an entirely new value to repeat over and over. An empiricist might say, next time I won't be fooled. I'll wait 1,000 steps instead. But I can easily fix these things so that nothing will happen for 10,000 steps, or 1 million, or 1 billion. I can make the burst after any finite number that bores you into an empirical conclusion. In chaotic dynamics, huge timescales must be expected for change, and they can be well beyond any classical thermodynamical timescales arising from things like ocean heat capacities. Dynamical systems are more than thermodynamic. Humans naturally look for an external cause for the jump, but there is no external cause. The intrinsic dynamics has just been not fully explored. We experience such things with weather. In fact, that's essentially what weather is. Bursts of wind and entire weather systems both seem to emerge initially from the nothingness that we blandly call instability. If we can't assume that the future will be like the past, empirically based models are in trouble. We don't know how well our fake physics will hold up in new dynamical regimes differing from the ones we know. This leads me to a crucial question about climate and climate change that I will get to by introducing my friend Larry Longwave. Larry Longwave lives large in the climate sense of the term. He's at least the size of Vermont, say, and his heart beats so slowly that a day's worth of heartbeats for us would take centuries or millennia for Larry to pump. What would it be like for him? Talking about it would be a very abstract exercise, but some people have made it more concrete for our purposes today because of their ultra-long exposure photographs. This photo by Justin Connell appeared in New Scientist on its website. It's an exposure of 6 months. It uses a technique called solar graphy, which utilizes a pinhole camera. In the photo, the bright streaks in the sky are a fixed structure that Larry Longwave would see instead of the sun. No traffic is visible. Larry is too large to see it, but even in his microscope, traffic is too quick for Larry to see. Larry misses some things that we would see, but he also sees things that we cannot. In Tarja Trigg's solar graph, the same bright structure appears in the sky. It's everywhere in Larry's world. The streets are empty, just as in the previous shot, but curiously, the parking lot is full. It's not full of any particular cars, it's full of recurrent visits of cars. They are like atoms in the materials making up our bodies. The material seems substantial enough, but individual atoms jiggle in and jiggle out without affecting the structures that they form. Suppose Larry calls the time for one of his heartbeats a second, then for him, a minute or two would be decades of our experience. For Larry, the solar graph is little more than a snapshot. He does not have to wait months like us to see it. A solar graph is what he perceives instantly, according to his reckoning. He would produce a sequence of them over his minutes to produce an animation. It would take us decades to produce it, but it would be like a short home video to Larry. What would such a video be like? What would Larry see happening while the overall structure of the bright streaks in the sky would be fixed? Larry would see parts of them brightening, dimming, and pulsating, probably not unlike we see in an aurora borealis. For Larry, there would be no day or night, and there would be no seasons, just this shimmering arch in a translucent gray-blue sky. Changes that Larry would perceive would be caused externally or internally. Either would be like climate change to us, but only the changes through internal dynamics would be like weather for Larry. What would Larry's version of the weather be like? People don't think much about Larry's weather. The conventional wisdom, rooted in models, is that there wouldn't be any. This is a diagram from the modeling chapter of the IPCC's fourth assessment report. It compares different model outputs in a power spectrum. Across the bottom are periods of time on a log scale. I'm not interested in all of those time scales. I'm interested in Larry's world. Let me illustrate it. Let's also stretch it out, since there's a long range of time scales here. It's amusing that the model curves differ in magnitude by a factor of 100. But as I said, things like that can be fixed. What cannot be fixed is that all of them are flatter than the Great Plains. There's a famous theorem by Wiener and Kinchin that tells us in such cases that the autocorrelation function is 0. In practice, that means that the model solutions will look more like the bottom of these two curves than the top one. That is, there will be no long-term trends, which means that on averaging out the small stuff, nothing much happens and things never change for Larry on their own. Thus, there's no Larry's weather in models. Stability in Larry's world is what defines a model climate state. That definition becomes de facto the definition of climate generally. But this unproven common wisdom could be wrong. As I said earlier, computational schemes can suppress real instabilities. Now that you understand the imagery of the treacherous steam engine with an unstable boiler, you will not be surprised that complex algorithms for nonlinear systems generally, not just for climate models, are often computationally unstable when pushed to extremes in time. For climate models, we saw it in the historical struggle against so-called climatological drift. That's a euphemism for spurious, long-term internal change in models. They believed it was spurious because model atmospheres did weird things over long times, like losing mass, which no one could account for, or returning negative densities, etc. In fact, one of the milestones in the UN's fourth assessment report is the creation of a kind of fake physics that finally made fictional energy flows, called flux adjustments, unnecessary to fix such things. So drift was interpreted as due to computational instabilities and was beaten out of the system from the beginning. What else could they do? They have no way, theoretical or empirical, to pick out real, long-term trends from computational instabilities, let alone to distinguish between externally and internally caused dynamics. All they had were the simplistic presumptions of early stochastic models and a desire to prevent their figurative boilers from exploding. Over time, it's become an article of faith that there's no Larry's weather, and the absence of same came to be what defines climate. But empirical models cannot determine whether Larry's weather exists, because we have very little direct experience with Larry's world, and we must anticipate very long timescales for internal change in complex systems. If Larry's weather does exist, then we must think again about what we mean by climate and climate change. Let me say it another way. The question is not what is causing climate change, but what climate change actually is. I'm sure the gods find this a laughing matter.